We are going to talk in my poster about power model for RISC-V processor. And the key idea here is that we design a set of characterization programs, indeed characterization generator programs, and then we evaluate Rocket on 2 different technologies down to placing route. So you can have these power tables, that's that green box on the top. And the key idea is that with these power tables, you can get whichever simulator or even software running on a higher level and create power figures about your software. So you can run your software in a regular simulator and get some pictures like this one with the power running through your software. So you have much more of this picture here, some results. You can get full power, and you can also simulate them and run regular programs using your infrastructure. So we plan to release these power tables and also the infrastructure required to generate that. I think I saved you 1 minute, so use these minutes to go to my poster. Thank you.
My name is Chris Celio. I'm still a grad student at UC Berkeley. And for my poster, what I'm talking about is the processor that I've been working on, which is now open sourced. It's written in Chisel. It's superscalar, out of order. It's completely parameterizable, so you can change your issue widths, your function unit mix, all that good stuff. And because it's in Chisel, it's actually only 10,000 lines of code and only grows very slowly. So it's pretty, not that hard to understand for just even a single person. And this is a part of the Rocket Chip SoC ecosystem. So if you've been playing around with Rocket and you like that whole setup, switching to Boom should be really pretty easy. It should really just be kind of a single config option to throw if you want to move from Rocket to Boom. Anyways, it's open source. I got my first pull request this semester. So that was really cool to get add some visualization to Boom. And I also have a design document, so you can read 60 pages of how Boom works and what my thinking was that went into it. And again, I accept pull requests, and I like hearing what other people think about it. Thanks.
Hi, I'm Palmer. I'm a grad student at UC Berkeley. I'm advised by Kirsten and Jonathan Bachrach. So I do some kind of RISC-V software development stuff, but kind of my day job, I guess, is building chips at Berkeley. So we have a lot of chip projects going on right now. We have the DSP-1, which is Hurricane, which used to be called Raven, which does a lot of on-chip DC-DC sort of stuff. We're doing a Firebox project, which is a rack scale server, which is probably going to be on TSMC's 28. And we're doing a radio baseband project, which is on TSMC's 16. So one of the things we're really focused on, because we have a small team and we're building so many different configurations, is this idea of agile hardware development. And the idea is that we want to be able to build lots of different chips from the same RTL and similar physical design stuff, all at without a lot of people. So I have a poster on this. You can come and talk to me about it after the dinner thing.
So hi, I'm Skylar Eldridge. I guess I just graduated from Boston University, just finished my thesis. I'm advised by Ajay Joshi, and I work collaboratively with Jonathan Apavu. So I'll save you a lot of the motivation. People care about neural networks, but basically what we have is if you're familiar with Rocket, as everyone's been talking about, we have basically a plug-in accelerator that deals with both multi-transaction. So basically it's a multi-context accelerator for dealing with neural networks. And then one backend for that, this backend called Dana, which accelerates sort of fully connected multi-layer perceptron neural networks. It's all open sourced on GitHub, and you can just drop it in, and it should work with Rocket and additionally with Boom. So I'd love to talk to you more about it. And additionally, if you're interested, check it out on GitHub. Thanks.
Hi, I'm Michael. I'm from Antmicro. I didn't used to be into cameras, actually, but turns out our company is building one. We've built this. So this is an actual product that's using RISC-V inside. We have a Z-scale, a chisel implementation of it, and it's used for configuring and controlling the sensor and generally communicating between all the modules in this design. You can see it's a highly modular and flexible and open design. You can actually find code for it around the internet, although full public GitHub release will follow later in the year. This is committed to be fully open source and open hardware, including the FPGA bit streams and everything inside. Also the hardware, so you could basically manufacture the entire thing on your own if you wanted. Today I'll be showing a slimmed down version of the camera because I had to fit in, the 8-kilogram limit of Lufthansa's cabin baggage. But you'll be able to see also live at the poster, in the poster room, and discuss this great product. We built this in a consortium of several companies. We and Micro are responsible for the software and FPGA stuff in the camera. So basically all the logic, all the intelligence of this. Yeah, so come see the camera. Thanks.
Hello, my name is Olof Kyngren. I work as an FPGA designer at a company called Comcom, specializes in radio communications, RF communications, and industrial IoT. I'm also director and co-founder of the Free and Open Source Silicon Foundation. But the main reason I'm here today is as the main developer of a project called FuSoC. And as you can see, FuSoC is a build system package manager for HCL code. And why do we need such a thing? Well, just as many people in here will say that the languages we use are very outdated for doing digital designs, I say that the way we distribute them is very outdated as well. What we have today is something that's very similar to software development in the early 90s, where everyone rolled their own build system and copied files into the repositories. And with FuSoC, I make it easy to reuse your cores. And I know that many projects, especially open source silicon projects, want to reuse cores or want to make the cores usable in other contexts. But the build system has limitations that make it hard. So with FuSoC, I aim to make it easy to reuse and share code. And I hope you come to see and talk to me about this. Thank you.
I'm Lauri Koskinen from Minima Processor. We're a startup from Finland. And our technology basically allows sub and near threshold operation for any digital logic. We modify the clocking. We modify the digital library, both quite minimally, and achieve very low, ultra low power. So some results here for the RISC-V. And here I'm basically looking for partnerships. So looking to define our product. Our business model is twofold. So at the moment we're taking customers' RTL, not RISC-V, anything else, or basically anything, and modifying that for ultra low power. At the same time, we're doing our own product based on RISC-V, and we really want to configure that so that is of interest to as many companies as possible. So please visit the poster, and I can tell you more about the technology. And another thing, this project has slightly roots in the Raven project, and that's interesting. It's nice to be here.
Hello, I'm Ranjani. I am from Morphing Machines, the company that was incubated at Bangalore, India, that was incubated at Indian Institute of Science, the logo you see in the left. We have a multi-processor solution, a little different from the others. That's what we believe in. And the current product that we have, which we have delivered to Safran, the defense company in France, is based on RISC-V. We have actually delivered a 128-node RISC-V multiprocessor redefined. And shortly we are going to deliver a 256-node redefined to Safran. What we claim is unique about us is we have taken a general purpose processor like RISC-V, but we have the ability to hook on custom-made hardware into our architecture and so perform like ASICs. Also, we have a compilation flow which will take an application program written in a high-level language like C and compile it to our architecture. And what we do at runtime is to pull in only the necessary resources to get the performance that is expected. So I don't have time to go into details of all the components, but I hope it's clear. We have a demo running at the poster session. What we plan to do is to remotely connect to the platform that we have back in India. What we have in India is a 128-node redefine emulated on several of Vertex 7 devices. And the application that we are going to show is you walk by the screen, your color image will be transformed into black and white. That's the best we can do with a remote connection. And if the frames are lost, let's blame it on Google Hangouts. Thank you.
Hi, my name is Tim Newsom. In January at the workshop, I presented a debug spec, and I promised an implementation. I'm going to demo the implementation. This debug is just run control. It doesn't include any trace like Wei was demoing. So basically, I'm going to show you can GDB, you can download code, you can run it, you can set breakpoints, change registers, look at memory, all that stuff. So if you're interested in debug, you should come talk to me. If you don't have time, check out the debug mailing list. URL is kind of at the bottom right of this slide. And I think that's all. It's all going to be open source, so you can all use it. Currently, we have a Rocket implementation, and that's it. Thanks.
Hello, everybody. I'm Davide. I'm Schiavone. I'm here for Davide Rossi. And please come to our poster to talk about Pulp, which is our parallel ultra-low power platform, which is programmable. And thinking about Internet of Things, we have to acquire data from sensors, then process them, and then send them to the external world. But most power consumption comes from the antenna. So we can exploit classification algorithms to reduce the bandwidth, but state-of-the-art microcontrollers are not able to provide such performance in the power budget between 1 and 10 milliwatts, which is a requirement for Internet of Things. So Pulp provides several hundreds of mega operations in the same power envelope. We are able to do that because we have access to the wall stacks, starting from the low-power silicon technology provided by STMicro, FDSOI. Then we make our processors and hardware IP. For instance, our processor is based on RISC-V. Then we have the wall compiler infrastructure, for instance, GCC. Then we provide a virtualization layer, and to make it programmable, we provide to the final user a support from OpenVX, CL, and OpenMP. And that's it. Thank you very much.
Hello, my name is Adam. I'm finishing my third year at Berkeley. I'm co-advised by Krista and Jonathan Backrack. And along with Colin Schmidt, we have been working on an automatic path coverage tracking for RISC-V processors. Everyone here is familiar with Rocket and Rocket chip. And as you know, it's written in Chisel, and it generates many differently parameterized instances. And they can execute a large RISC-V test suite, but what percentage of the design is actually executed by that test suite? We didn't really know, so we were curious. What does percentage mean? We defined it as path coverage, which if you're familiar with Chisel, there is a sort of if-else construct in the language. We wanted to make sure that both paths, the true and false path, were executed in every module, in every instance generated by the design. Now, it doesn't ensure a correct design, but it's the first sanity check that makes sure that, okay, things are working. And so we augmented the Chisel compiler to add this instrumentation. We generate these cool histograms and graphs, and we can tell which paths aren't executed, and in your source code can point to exactly where you need to, where it's not getting executed. We also looked at Torture, which generates random assembly sequences. And we were curious to know whether that increased or decreased coverage. How did that compare? And finally, we have Huacha, which has been discussed before, but that's a custom coprocessor. And we sort of did a case study where we used this tool to improve our test suite. So if that interests you, come to our poster. Thank you.
So hello, my name is Martin Trübel. I'm from the Technical University of Denmark. And currently my main interest is to use RISC-V in teaching. So I'm teaching bachelor level computer architecture, base computer architecture, and at master level advanced computer architecture. I've already used some exercises with RISC-V in the small simulator in the advanced course, and I'm thinking about switching to the RISC-V in the base bachelor level course. But this is more actually a call for cooperation between some of you teachers and to share slides or share also material. Okay, sorry. And we also need some addition to the standard textbooks, which covers RISC-V instead of MIPS or ARM at the moment. It's kind of work in progress, and we can discuss it during the breaks.
Hi. I'm Howie Schroeb from MIT, CSAIL. This is a project called P-Taxi. It's a follow-on to a project we did last year. These are explorations in cybersecurity enforced in the hardware by tag extending the machine. Very similar in spirit to the Dover project that Andre DeHaan will talk about tomorrow. But here we're using a very small tag to see how much we can get out of it just by data type tagging the machine. And I'll be happy to talk to anybody about the details later on.
All right. Okay, so I'm not Drake Smith, and who'd want to hear from him anyways? But I am with Secure RF. Anyways, so just to fill in some blanks, we were fortunate to get to do a presentation earlier today. We're focused on developing authentication and cryptography that fits on very, very small, low-powered, low-resource devices, and RISC-V looks like a great target and platform for us. Specifically, we target 8 and 16-bit platforms, typically 32-bit, where the standard crypto stuff does not run. Big part of what we do is authentications, and to fill in some blanks from earlier, things like the automotive industry and smart grid, where you need not hundreds but thousands of authentications a second, is one of the places on low resource FPGAs where we do put our methods. And we are active at NIST as we speak, at the NSA 3 times in the last 2 years, and just finishing a DoD project in terms of our platforms. We're published, we have tools, we'd love to work with people. We'll be demonstrating some of the code that we've talked about on a micro-semi platform over at the presentations, and welcome anybody to come by to talk about getting an eval kit. Thank you.
All right, my name is Ted Spears, and I brought along Ted Moreno with me. So you said one slide per presenter, but we got 2 Teds per slide, so I think that's important. Anyways, point here, Microsemi is a big believer in RISC-V, and as you can see, we're a major sponsor of the tutorial tomorrow. And we're committed to the creation of a thriving RISC-V ecosystem. Bottom line, we kind of believe your success will translate to our success. So we want to kind of work with the community to forge a thriving RISC-V ecosystem. And so we're in the process, the result of defining a RISC-V roadmap, not only obviously for our FPGAs, but we're a company that's much bigger than FPGAs, and RISC-V is making progress inside the larger company as well. So bottom line, we'd love to meet you. So come by our booth and share your involvement in RISC-V. Talk to us about how you'd like to see the ecosystem develop. And you can also learn about the hardware that's going to be used tomorrow in the tutorial that we're sponsoring, and learn about the FPGAs that are in that hardware, which we think are an ideal platform for a lot of the new markets that are going to be emerging, where we've got security, low power, reliability. These are all applications that can benefit from an open architecture like RISC-V. And finally, the reason I brought Ted, he'll be handing out swag at the booth. So the first 100 visitors will get a Microsemi laptop bag.
All right, just quickly, I'm Marko Zec from University of Zagreb, and I'll do a poster about the homegrown FPGA optimized core, which apparently does quite well in synthetic tests, beats Microblaze, Nios, and Cortex by a healthy margin. And interesting thing is that the pipeline can be retargeted to execute RISC-V. RISC-V synthetic benchmark figures are much lower. If you are interested in hearing why is that and which techniques have been applied to achieve a balance between high instruction throughput and quite low lookup table utilization, well, please stop by and have a chat. That's it.
My name is Lei Zheng, so I'm lucky to be the last one for this part.
You've got a half an hour.
Thank you very much. So my name is Lei. So I'm from China. I'm working in the Institute of Computing Technology, Chinese Academy of Sciences. So we are using the RISC-V hardware and software components to build for the edge computing system. So the edge computing is the computing on the edge, like IoT devices or wearable devices. So we believe that RISC-V has bright future in this area because not only because the RISC-V is open and free, but also we think that the devices and the chip types in this area is quite fragmented. So an open ISA is more suitable for this trend. And also in this area, we don't have some, legacy burden. So we believe that RISC-V will be successful in this area. So we focus on this. And what we are doing is that we use the RISC-V core to build an SoC. We add two features in this SoC. The first one is that it's always on sensing because we think that in the edge computing, the device should always sensing the information around it. And second one, we add a neural network accelerator to understand what is happening around it. Because we think that for edge devices, it has, to some extent, have some intelligence to know what happened. We do not want to deliver all information to the cloud to do some recognition stuff. So this stuff is now running on the micro semi FPGA, and we use it to build a lot of devices. We are now working hard on verification of this thing. So we try to tape it out by the end of this year. So that's it. See you at the poster. Thanks.